Yeah, great. Yeah, thanks so much for inviting me to speak at this conference. I've been learning a lot and enjoying a lot of the talks. But yeah, so today I'm going to talk about I'm not the rational dualizing module of out of Fn. This is joint work with Jeremy Miller, Sam Nariman, and Andy Putman. And the thing that I sort of want you to take away from my talk today is there's this nice sort of correspondence or sort of parallels between SLN of of a number ring, or in particular Z, and out Fn, the automorphism group of the free group on n letters, where oftentimes one of these groups will have some construction or property or result, and oftentimes it'll be the case that there'll be an analogous kind of thing for the other group. And so if one of your groups has some nice property, it's a reasonable and good question to ask if the corresponding thing holds for the other group. And oftentimes that's the case, but occasionally this analogy breaks down. But I'm going to start out by just telling you about two things that both of these groups have in common. If you watched Peter and Jenny's lecture series, this is going to sort of relate a lot to what they were talking about. So the first thing is something I guess I'll call rational duality. And the next is, and this is just a property that both these groups have. And then the other thing, another thing that you can do with both these groups is a construction called Steinberg modules. So you can sort of construct some module that both these groups act on in some sense. But yeah, so let me start by telling you about rational duality. So a group G is a rational duality group if there exists a non-negative integer nu and Q adjoin G module D such that for any non-negative integer I and Q adjoin G module M, we have an isomorphism from the cohomology in degree nu minus I of G with coefficients in M to the homology in degree I of G with coefficients in M tensored with D over Q. This number nu that I just wrote down, this is called, I guess I'll call this the VCD, or the virtual cohomological dimension of your group. And this Q adjoin G module D, this is called the rational dualizing module. So you can sort of think of this. So if your group has this property, you can sort of, it's a very nice sort of property that your group can have you can sort of think of it as being like, in topology, there's this notion of Poincar duality, which relates the cohomology of the space to the homology of the space. And you can sort of think of this definition as sort of an analogous thing, but for groups where, after some sort of twisting, you can relate cohomology to homology. And so this is really like nice for calculations. And furthermore, we have like an explicit description of like what D is in general. So if this rational dualizing module exists, then D is isomorphic to the cohomology in degree nu of G with coefficients in Q adjoin G. So yeah, and so even though we have this explicit description of the rational dualizing module, in general, it helps to have like another sort of model for doing calculations in practice. It helps to have like another model for the rational dualizing module. Yeah, I mean, like, I'll give you an explicit example of like what I mean, in a few minutes. But if you watched Pew and Jenny's talk, this is just the Steinberg module for SLNZ or something, but or SLNR. But yeah, so it's a theorem due to Bestvina and Feighn that out of Fn is a rational duality group. As a result, we can sort of we have this we can sort of describe, like, at least like in certain ranges, what the homology, the rational homology of out of Fn looks like. So this this graph I'm about to draw is supposed to sort of represent some range, or for some in some degrees, like the rational homology of out of Fn with and so the vertical axis is going to be the homological degree, and then the horizontal axis is going to be n. And so this straight line that I've just drawn is the line I is equal to 2n minus 2. And this is just the same thing as the VCD of out of Fn. And so since out of Fn is a rational duality group, if I is above the VCD, then these homology groups are going to vanish. So this is 0 everywhere above this line. And then here's another line, and this is the range n is equal to 5 times I plus 1 over 4. And for any any values below this line, we're going to have that the homology is 0. And this is by work due to Serre and Galatius. Something I should say, I forgot to mention, is that the line I is equal to 2n, or that the VCD of out of Fn is 2n minus 2. This is due to Color and Vogtmann. But what I want to sort of emphasize is that there is a region, a non-trivial region, where we don't actually know that much about the homology. So in this region here, there's a lot that's unknown. We know from some like computer calculations that there's some like low degree homology classes. For example, I is 7 and n is 5. There's a non-zero homology class, but we don't have know that much. Something I think that a lot of experts in this area would be interested in is to like have an infinite family of homology classes. So since Peter had like a session where he just suggested like open problems and stuff, I feel obliged to give an open problem. So the problem I'm going to propose is, and I mean, this problem is not, I'm not the first one to come up with this problem, but it's to find an infinite family of non-zero homology classes in the homology of out of Feighn. So here n can vary and stuff. But yeah. But yeah. So so out of Feighn is a rational duality group. It's similarly, it's a theorem of Borel and Serre that for R a number ring that SLN are, so the linear group is a rational duality group. Something I should say, I guess, is Borel and Serre, they do a little bit better. They also give, a post-set sort of model for the rational dualizing module. But before I say more about that, that module, let me just sort of draw what the, let me just sort of draw like a similar graph for the homology, the rational homology of SLNZ. So on the line, this is supposed to be a parabola here, or half of a parabola, and this is the line I is equal to n choose 2, and this is the VCD of SLN Z, and above this line you're going to have the homology vanishes. And yeah, so as I mentioned, Borel and Serre also provide like a posted model for the rational dualizing module, and this is different from out of Feighn because for out of Feighn, Bestvina and Feighn, they don't give you a similar sort of some posted model. They just prove that's a rational duality group. So let me give some sort of really nice, just state some really nice results that one gets from Borel and Serre's description of the rational dualizing module, because I think these are both really great results. There's a theorem due to Quillen who showed that, so here R is a number ring, and Quillen showed that the algebraic K groups of R are finitely generated groups for all I. And then let me just mention one other result, and this is sort of a compilation of work of 3 people. And yeah, so this is Lee and Sharba, Church Putman, and Benjamin Brook with Jeremy Miller, Peter Potts, Robin Schroka, and Jenny Wilson. So these people showed that for n at least 3 and I equal to 0, 1, or 2, that the cohomology in the VCD of, or sorry, I should say the cohomology in degree n choose 2 minus I of SLNZ with coefficients in Q. This is isomorphic to the homology in degree I, since n choose 2 is the VCD of SLNZ. So they showed that, so this is isomorphic to the homology in degree I of SLN with coefficients in the rational dualizing module. And they showed that this vanishes. So the case I is 0 is due to Lee and Sharba. I is 1 is due to Church and Putman. And then recently the 5 author group proved it for the case I is 2. And yeah, and everything sort of really depends on Borel and Serre's really nice sort of post-set model for the rational dualizing module. So yeah, I've been sort of hyping the rational dualizing module in this case, so let me just tell you about that. And so to do that, I have to tell you about the Steinberg modules. Yeah, so so M here is an R module, and I'll say that a submodule N of M is a summand if there exists another submodule C of M such that M is equal to the disjoint union of N and C. And so I'll use the notation tau of M to denote the Tits building on M. So this is just the geometric so it's just a space that you can assign to this to a post set. So it's the geometric realization of the post set of non-trivial and proper summands non-trivial proper summands of M, and the post set is ordered by inclusion. Now, it's the theorem due to the Solomon and Tits theorem, due to Solomon and Tits, that for are a Dedekind domain that the Tits building on Rn is homotopy equivalent to a wedge of infinitely many n-2 spheres. So it's just a bunch of spheres in dimension n-2 attached along some common base point. And so we can define the Steinberg module on Rn to just be the reduced homology in degree n-2 of the Tits building on Rn with rational coefficients. Something I should say about this module is that it's a Q-adjoin SLN R module, and this just follows from the fact that the special linear group is a subgroup of automorphisms on Rn, and so it's going to permute summands of Rn. So this induces an action on the Tits building, and so you get an action on the homology as a result. When R is Z, there's a really nice presentation of Steinberg of Z to the N due to Bykovsky. So Bykovsky showed that Steinberg of Z to the N has generators of the form given by symbols V1 through Bn, where V1 through Vn is an ordered basis of Z to the N. And then it has three relations. The first relation is if one multiplies any basis vector by plus or replaces a basis vector vi with plus or minus 1, so you multiply it by up to a sign, then this is the same symbol as before. So you get V1 through Vn. And then the second relation says that for any permutation sigma in the symmetric group on n letters, if you apply sigma to the indices of V1 through Vn, so if you consider the symbol V sigma 1 through V sigma n, this is the same symbol up to sign as the symbol V1 through Vn. And then the last relation is called the Manon relation, which says that V1 through Vn is the same as V1 comma V1 plus V2, and then V3 through Vn plus V1 plus V2 comma V2 through Vn. Yeah, and so I said that the Steinberg module was a construction that you could do for both of SL and R and for out of Fn. So let me just tell you what the analogous thing is for out of Fn. So instead of a module, I'm going to let G be a group. And I'll say that instead of a submodule, I'm going to take a subgroup of G, and I'll say that it's a free factor if there exists another subgroup C of G such that G is equal to the free product of A and C. And so, and that we can define the Tits building on a group to just be the geometric realization of the poset of non-trivial proper free factors of G ordered by inclusion. And analogous to the Solomon and Tits theorem, we have the following theorem due to Hatcher and Vogtmann. And they showed that the Tits building on the free group also is the homotopy, is also homotopy equivalent to a wedge of n-2 spheres. And so one can define the Steinberg module on Fn to just be the reduced rational homology in degree n-2 of the Tits building on Fn. And for the same reasons as before, the Steinberg module has an action of Q adjoin out of Fn on it. So something that we proved is that Steinberg module of Fn, so we showed that the Steinberg module of Fn has an analogous presentation to Steinberg of ZVN. So it has generators, symbols of the form V1 through Vn, where the set V1 through Vn is an ordered basis of Fn, and the relations are exactly what you would expect if you, instead of multiplying an element by plus or minus 1, now we just have to consider an element up to like inverse. So if we raise a basis element to plus or minus 1, then we get the same symbol as before. Relation 2 is exactly the same. And then for the monorelation, relation 3, instead of adding basis vectors, all you do instead is you just multiply them together. So V1 times V2 is all that gets changed. So you should sort of think of like this theorem is sort of saying that Steinberg of, out of Fn is sort of like Steinberg of like a really nice like Euclidean domain and stuff. And yeah, and so as I mentioned before, so the reason why we care about the Steinberg module is, or I guess one reason why you should care about the Steinberg module is Borel and Serre's result, this result of Borel and Serre, which is that for R, a number ring, we have that Steinberg of Rn is the rational dualizing module of it's the rational dualizing module of SLNR. And so motivated by this theorem of Borel and Serre, Hatcher and Vogtmann asked the following question. So they asked, is Steinberg module of Fn the rational dualizing module of out of Fn? And so we give a partial answer to Hatcher and Vogtmann's question. But before I do that, I should state like our main result in our paper. So we showed that for n at least 2 and I equal to 0 or 1, that the homology in degree I of out of Fn with coefficients in Steinberg of Fn. So we showed that these homology groups vanish. And so as a corollary, we showed that Steinberg of F5 is not the rational dualizing module. Of out of F5. So let me just quickly, the proof of the corollary is actually not that hard, so let me just give it to you. So, so there's a theorem, so I guess I should say that, as I mentioned earlier, Culler and Vogtmann showed that the VCD of out of Fn is equal to 2n minus 2. And then there is, I also mentioned earlier that there's this calculation, and this is Gerlitz, who showed that the cohomology in degree 7 of out of F5 with Q coefficients is equal to Q. So now by our theorem, we have that the homology in degree 1 of out of F5 with coefficients in Steinberg of F5 is 0. And if Steinberg of F5 were the rational dualizing module of F5, then we would have an isomorphism to the cohomology in degree 2 times 5 minus 2 minus 1 of out of F5. And here I'm taking Q coefficients, but this is just equal to 7. So we have this is Q, and so we have a contradiction. So maybe two things I should say here are that we don't know in general if Steinberg of Fn is not the rational dualizing module of out of Fn. Part of this, I think, is just because we don't have that many calculations actually of the homology of out of Fn, but we conjecture in general that, except for maybe some low degree cases, that the Steinberg module of Fn is not the rational dualizing module. And then something else I should say is that my understanding, at least amongst the experts, is that there isn't like a clear candidate for what the rational dualizing module of out of Fn should be or is. And so you know, if someone can figure that out, that would be really cool. Yeah. And I think I have like less than 10 minutes, so let me just with the remaining time I have left, let me just say briefly how we prove, or let me just give like a really short sketch of for proving the main theorem. And I'll just give you sort of like basically I'll break it up into 3 steps, and the point is, I'm not going to like give you the full details. I just sort of want to give you the point of this is just to tell you that if you know how to prove that the homology in degree, if you know how Church and Putman's proof that the codimension 1 cohomology of SLNZ vanishes, we do an analogous sort of thing for showing that for getting our theorem. So so the idea is, the proof strategy is basically we sort of model the TITS building on Fn using like a highly connected simplicial complex S. And highly connected here just means that the homotopy groups of S are equal to 0 for I less than some like constant, I think it's like n-2 maybe or something. And maybe something I should say about this is that this this comes from a certain simplicial complex that one gets on when like studying a certain kind of 3 manifold. So this simplicial complex comes from, I'll just say it comes from a connected sum of S2 cross S1s, and then you remove some finite collection of disjoint disks in your space. And yeah, and so so this is sort of this is like the hardest part of the proof, in my opinion. It's definitely like the most natural, at least for me it was. And then the other 2 steps are somewhat more straightforward. We use this simplicial complex to get a presentation of Steinberg so I think of like Gn as just sort of being like generators of Steinberg, and Rn is sort of giving you your relations on Steinberg. But sort of the thing I want to emphasize here is that these are flat Q adjoin out of Fn modules. And so it follows that the homology of out of Fn with coefficients in Steinberg of Fn is equal to the co-invariance of these 2 modules that I've written down. So it's equal. So it's equal to the co-invariance of Gn with respect to the out of Fn action for I is equal to 0, And these are for I is equal to 1. These are the covariants of the relations of Rn with respect to the out of an action when I is 1. So in case you don't know, so for M a Q adjoin G module, the covariance of M with respect to G is just the quotient modulo you get of M modulo G times M minus M. So here, this is for all G and G and little m and big M. So, so the last part is we just have to show that these covariants vanish and this gives you a result. And maybe I should just like conclude by saying, like, if you are familiar with Church and Putman's argument, steps 2 and 3 are entirely like the same as what they do. So that part is like really straightforward. It's just the first step, which is definitely like the hard, like the non-trivial part of our argument. That's all I wanted to say. Thanks.
Okay. So, any questions or comments? No question on the chat room. So, just to be sure, what is the difference with the strategies that you use for automorphism of free group and the one which is used in the SLNZ case?
Yeah, so the main difference is the step 1 here. So Church and Putman, maybe I should say it like this. So for the Tits building on Z to the N, Church and Putman introduce some Church and Putman, I guess, like give some simplicial complex I guess you should think of they introduced this complex called BAN, which is augmented partial bases on Z to the N. So these are defined purely like from algebra. So these are defined like these are like subcomplexes coming from Z to the N. So it's a purely like algebraic thing. If you want, I can write them down. So Bn, well, I shouldn't write down. Bn is the complex of partial bases where a vertex is given by a partial basis of Z to the N. So it's just a collection of vectors such that you can adjoin some other vectors and get a basis of Z to the N. And BAN is like an augmented version of that, where you can allow partial bases, and then you can allow some extra vertices as well. Our sort of, what we do is we sort of have to construct like something analogous to BN and BAN, but for for like a simplicial complex coming from a space. It would take me a few minutes. I don't know if I should go into more detail about that. Maybe I should say like, I probably shouldn't say more about what that is. But yeah.
No, it's okay. I mean, because in fact, in the summer school, in the previous week, in the lectures of Peter Patz and Jennifer Wilson, so they explained the BAN. So in fact, my question was to relate to this construction and to see more precisely what are the difference between this construction and the hot free Fn construction.
Okay, I can maybe say like briefly what it is for Fn, because I think it's definitely like a little bit different. The idea is, yeah, okay. So I guess like, so I mentioned before that you want to sort of consider a connected sum of S2 times S1s with, I don't know, I is equal to 0 to n, and then remove some like finite collection of disks on your surface, or on your three manifold. So I'm just going to sort of draw what this looks. I'm going to pretend that we're living in the world of two manifolds. So you can sort of think of this connected sum. Let me just call this space M and B. And so like, here's how you can sort of pretend that we're living in the world of two manifolds. So this is sort of a picture of like what M21 looks like. You can sort of imagine that if I draw like a circle like this is sort of like an S2 inside your surface instead of S1. And if I drew like a circle horizontally like this would sort of be like an S1 somehow. But anyway, so the idea is, so we have this like a three-dimensional manifold, and you can consider like a complex of sphere systems on it. So what you want to sort of look at is basis elements are sort of corresponding to non-trivial spheres embedded in your manifold. So we allow, for example, like a sphere like this. This is okay. This is okay. But we wouldn't allow, for example, a sphere here. Like if you could put some disk here, this is not okay. And similarly, because you have spheres that this sort of bounds the boundary, this one is not okay either. But anyway, so the thing I guess I want to observe here is that the fundamental group of M and B is isomorphic to the free group Fn. So the idea is from, like, I haven't told you what the simplicial complex is yet, but the idea is from these spheres that are okay, you get a map on which, like, I'll just say, like, you get a map to the free factors of Sn, I'm sorry, of Fn. And so given, I won't say what it is in general, but the idea is just, so in this picture here, you will send like this example to the fundamental group of the surface that you get, or of the space that you get, by removing these spheres that have a check next to them. So yeah. Yeah, so you get the fundamental group of this, and this is going to be a subgroup. This is going to be a free factor of Fn, is all I'm trying to say. And so, like, you should think of this as giving you, this is sort of the analogous thing to like the complex of bases on Fn, or on Zn. Sorry, that was a long answer, and I don't think I explained it well, but yeah.
Okay. So it means that we have no dualizing module, but nevertheless, let's say the Steinberg equivalent is behaving like the one in the arithmetic case.
Sorry, can you repeat that? I missed the first part.
So despite the fact that we have no dualizing module, the homology of the automorphism of free group with coefficient with the Steinberg modules behave at least in a lower dimension as the one in the arithmetic case.
Yeah, I mean, there is, the point is, I guess, is that like there is like a notion of the Steinberg module, but it's definitely not the rational dualizing module in this case. Yeah.
Okay, very interesting. No comment, no further comments? Nothing on the chat. So thank you again, and thank you to all the speakers of the